Okay, so we're looking at lesson 3.6, polynomial applications. Before I begin this, let me just say that I'm planning on having a test over Unit 3 on Wednesday next week. Wednesday next week will be the test. We'll review Friday and Tuesday. Y'all have a day off on Monday. So we'll have review stuff to work on Friday and Tuesday, and then test on Wednesday. Okay? Okay, so we've got some kind of similar problems here, three similar problems in that we're trying to maximize volume of a package or a box or something like that. So for the first one, it's the open box. An open box can be made by cutting out squares from the corners of a 9-inch by 12-inch rectangular sheet of cardboard and folding up the sides. So I have a rectangular piece of cardboard. It's 9 inches by 12 inches. And what we're going to do is we're going to cut little squares out of each corner, and then we'll fold up the sides, and we'll have what's called an open box. All right? And I want to maximize my volume, and so all of these are going to be the same length I'm cutting out. They're squares, so they're the same on both sides. Okay? So when I've cut it and folded up, what's going to be the situation? Hopefully you can visualize this, but what's going to be the situation is that the base of the box will go across here. Right? This will be like the base of the box. Okay? So this length would be, the whole thing is 9 inches, but we're going to cut x off this side, x off this side, so this is 9 minus 2x. Going across here, it's 12 inches, but we're taking off x and taking off x, so this is 12 minus 2x. And then the height of that box will just be x. Where I fold it up, it'll be x inches tall. So my function is, let's call it v. V of x. V for volume. And I'm going to have 9 minus 2x times 12 minus 2x times x. All right, and I'm fine with leaving it like that. We don't have to expand it, all right? So the domain. The domain is going to be, clearly it has to be, I'm going to have to cut off more than one, so I'm going to say 0 to, and the most I could possibly cut off would be 4.5 inches, because this is 9 minus 2x, and so if x is 4.5 inches, then if I can't go beyond 4.5 inches. If I go up to 4.5 inches, I'm cutting the whole thing. All right, so it's 0 to 4.5 really. Okay, so when I make my window, I'm going to set my window from 0 to like 6 or so, because that's it. And I kind of graphed it, and you can see this will be easier to do on Desmos, I think, but when I zoomed out on it a couple times to look at it, and I could see that the maximum was less than 100. So if we think about the top of this as being 100, then the graph of this, it's going through 0, 0, and it does this, and then it comes down, and it actually goes through right at 4.5 here. All right, and so my range, you know, my range is going to be from 0 to, let's see what the top number is here. So second trace, I'm going to find my maximum. I'm going to go down to hit second trace number 4, but again, this is easier on the Desmos. And I'm going to set my left bound and right bound here, so left of the maximum, and then I go to the right of the maximum, and I get a maximum value of 81.872. 81.872, and that's going to be my range here. Okay, so what is the maximum volume that can be enclosed? Well, that's it, 81.872, and that's going to be cubic inches. And what are the dimensions that will yield the maximum volume? Well, that's when x is equal to 1.697 approximately. So my height of the box is 1.697 inches. Okay, the length let's do 12 for the length. Let's call that the 12 inches. So it would be 12, let's get out of here, 12 minus 2 times 1.697. And for that, I get 8.606 inches. And then for the width here, I'll do 9 minus 2 times 1.697, and I get 5.606 inches. And when I multiply all three of those together, it should be pretty close to 81.872. There may be a little bit of difference just because of rounding, but it should be pretty close. Sorry, I went off the screen there, but there you go. Okay? All right. Next problem, a box with a lid. This time they drew the diagram for us. Two congruent squares are removed from one end of a rectangular 10-inch by 20-inch piece of cardboard. So this is 10 inches going this way, and this is 20 inches going across here. Two congruent rectangles are removed from the other end as shown. Determine the value of X so that the resulting box has maximum volume. All right. So this area right here is the lid of the box. Oh, and this is the base of the box. Okay? And then these rectangles are the same. So this is the same width as this, and this is the same as this. So what that tells me is that this is like the center piece. You know, this is like a center line for going left and right here. Okay? There's this part over here is the same as this part over here. So that means that this is 10 inches on this side and this is 10 inches on this side. And so the volume of the box, the base of the box here, this is going to be 10 minus a single x here. Okay? Going this way though, it's going to be 10 inches minus 2x. Alright? And then the height is still going to be x. When I fold that up, you know, this is my x and this is my x. So that's going to be the height of the box. So my volume as a function of x is going to be 10 minus x times 10 minus 2x times x. My domain this time is going to be from 0. I can't, you know, I got to cut off something, so it's got to be greater than 0. And then 5 is the most I can cut off here. I could go up to 10 for this side, but I can only cut off 5 inches. If I'm cutting from this side and from this side, I can only cut off 5 inches. So it's got to be between 0 and 5. So let me see if I can graph this real quick. 10 minus x, 10 minus 2x times x. I can see that I'm using the same window that I had last time, and that's actually pretty good. I mean, it's giving me a pretty good, nice window here. So my graph, again, I'm going to 6 and I'm going to 100, but it's not quite as low as the last one, but it's pretty good, and it crosses at 5 here. So let's do our maximum second trace max, number 4. And I'm going to go left, I'm going to go right, and I get a maximum of 96.225, and that's also going to be my range here, is going to go from 0 to 96.225, including that. Alright, what are the dimensions which yield the maximum volume? This time my x value at the maximum is 2.113. So that is the height of my box. It's about a little over 2 inches tall. Let's call it the length going across, 10 minus 2.113. So that's 7.887 inches. And then the width, 10 minus 2 times 2.113 is 5.774 inches. Okay, and once again, nice check, if I multiply these together, it should be about 96. I've got 8 times 6 is 48 times 2. It seems that's pretty close. Okay? All right, last problem. The package. The package may be sent by mail only if the sum of its height and the perimeter of the base is not more than 72 inches. Find the dimensions of the box of maximum volume that can be sent if the base of the box is a rectangle with a length equal to 2 times its width. All right, so let's say I have, here's the base of my box, and here's my width, and then this is twice as much, 2 times the width. Okay, and then here and here. So here's my height here. Okay, I know that the perimeter of the base, the sum of the height and the perimeter of the base is not more than 72. So the perimeter of the base is the distance around the base. So that's going to be W plus W is 2W plus another 2W is 4W plus 2 more W is 6W. So we're going to say height plus 6W is equal to 72 because we want to maximize that. So I'm just going to set it at the biggest number it could be. And so I'm trying to solve for my height here. And so height equals 72 minus 6W. So my function to get the volume here, my function volume of, we'll put it in terms of W here, is going to be 2W times W times 72 minus 6W, that's my height. Alright, this time my domain is going to go from 0. If I put 72 minus 6W equal to 0, I think that's going to be 12. So it has to be somewhere between 0 and 12. It's going to go back to 0 at 12. Somewhere between there I should have some kind of maximum. So let's graph this. I think this one's going to be pretty much bigger than the others. So 2x times x times 72 minus 6x. And so I want to definitely expand my window from -1. I'm going to go up to like 15 here. And I think I'm going to have to go a whole lot higher. Okay, so it went up and then it came back down at my 12 here. And I can see I need to zoom way out here. So I'm going to go, instead of right now my max is at 1000, I'm going to make that, 100. I'm going to change that to 1000 and just see if that's even anywhere close. Alright, it looks better. Still pretty much higher though, so I'm going to go up to maybe 3000. Let's see what that looks like. 3000. Oops, I did something wrong there, I think. Definitely did something wrong. Let's see. Oh, that should be -1, 15. And this should be 3000. Almost got it. It's just a little bit higher than 3000. So let's go up to 3500 and that should do it. 3500. So that gives me a pretty good picture here. So if I have 3500 here, I've got, and this is crossing at 12. Okay, I'm going to find my max here, second trace 4, have my left bound, right bound, and I get the maximum at 3072. So So what is the maximum volume? That would be 3,072 cubic inches. And this happens when x equals 8. Almost exactly 0.000000 and some other numbers. Alright, so my height is, well, I'll figure out the height in just a minute. My length is 2 times 8, so that's going to be 16 inches. My width is 8 inches. And then my height is 72 minus 6 times 8, 48. So that gives me 24 inches. Okay. All right. Oops, I'm off the screen there. There we go. Okay. So, I went through that pretty quick, but there you go. If you have questions, let me know. Otherwise, I will talk to you later. Bye-bye.